I am Hayata Yamasaki, working as an associate professor in the University of Tokyo. This talk is about the generalized quantum Stein's lemma and the second law of quantum resource theories. The talk is based on a joint work with Masato Hayashi in Chinese University of Hong Kong, Shenzhen, and other institutes. I'll start with background. Our human society has progressed as the technology evolves. And behind this technological evolution always is a strong theory that supports the technological advances. In the 19th century, we have a technology of steam engine, and the theory of thermodynamics is a physical theory that supports our efficient energy use ever since. And at the core of this thermodynamics is the second law, which characterizes the convertibility between thermodynamic states under adiabatic operations. And this is fully determined by a single function called entropy. It says that thermodynamic states can be adiabatically transformable if and only if entropy does not increase. And the important thing is that for any two states where entropy does not increase, we can always find some adiabatic operation. The second law of thermodynamics characterizes the state convertibility by a single function, entropy. And this is a very strong theory. And that beautiful theory of thermodynamics this is a foundation of this beautiful theory. But now we are in the 21st century. We have a technology of developing quantum device. And the quantum information theory is a theory that supports our quantum technology. Quantum resource theory emerged as a unified framework to explore advantages and limitations of quantum mechanics. And the quantum resource theory is characterized by determining a class of operations called free operations. This is a subclass of CPTP maps. So in the case of entanglement theory, this is chosen as a local operations and classical communication, or LOCC for short. But we can define many different theories, such as in the resource theory magic, this can be chosen as a stabilizer operations. Then free states are defined as states that can be obtained from any potentially non-resourceful initial states by using some appropriate free operations. Any state that is not free is called resource states, and this will be useful to assist free operations to achieve some information processing tasks. In this way, quantum resource theory studies manipulations and quantifications of quantum resources from these operational approaches. A canonical example of quantum resource theory is entanglement theory. It's an entanglement theory. So entanglement is a resource to assist local operations and quantum communication, and the task that we can perform with entanglement includes, for example, quantum teleportation. A separable state is defined as a set described by a convex mixture of product states, and anything that does not decompose in this form is called entangled state. But to conduct useful tasks in communication scenarios, in many cases, we need a particular form of states, such as a maximally entangled state. It's called E-bits. While in the lab, we usually have some general mixed state that is represented as rho. So in this case, it is important to convert mixed state into pure states, like E-bits. And this task is called, such an asymptotic conversion task is called entanglement distillation. And its optimal rate is called distillable entanglement. An equally important quantity is, I should use this one. An equally important task is its inverse task called entanglement dilution, which is the task to obtain as many rows as possible from many copies of E-bits. And its optimal cost is called entanglement cost. And one central goal in entanglement theory is to clarify optimal protocols and fundamental limitations in manipulating entanglement. In more general, conversion rate between row 1 and row 2 under some choice of free operations, such as LOCC, is defined as a primum of the rate to convert many copies of row 1 into row 2 up to asymptotically vanishing errors. And in view of success of thermodynamics, it is desired to have some strong universal law analogous to the second law. If such a law holds, the asymptotic conversion rate should be fully characterized by some single quantity describing the amount of resource in the state, such as entanglement measure. If such a second law should hold, then that would imply that disturbed entanglement and entanglement cost should coincide. But there's a challenge in formulating such a framework due to the irreversibility of entanglement conversion. Under the LOCC, it is well known that we have a bound entangled state, that is an entangled state. So its entanglement cost is non-zero. But this mixed state, from this mixed state, this mixed state cannot be distilled into pure entangled state. So its disturbed entanglement is zero. So inherently, these two are different for bound entangled states. And under LOCC, entanglement theory is irreversible. If you're only interested in LOCC, in entanglement theory, this is the end of the story. So it's over. Now, entanglement is irreversible. But if you recall the thermodynamics, we can also define operations in a more axiomatic way. So it may be reasonable to consider other classes of operations to make a more beautiful theory with some irreversibility holds. But it's still challenging in general to formulate such a irreversible theory for entanglement. Even if consider PPT operations, that is even stronger than separable operations, and of course stronger than LOCC. It is known that disturbed entanglement and entanglement cost under PPT operation does not necessarily hold. Even if we consider non-entangling operations, that does not generate entanglement. Disturbed entanglement and entanglement cost is in general not equivalent. So the central challenge here is that we need a more non-trivial relaxation of operations to formulate such a reversible framework of quantum resource theories in general. So that provides a motivation to consider generalized quantum resource theory, the generalized quantum Stein's lemma. So the only non-promising way to formulate such a general reversible framework has been to axiomatically define a more relaxed set of operations tailored for asymptotic scenarios, as originally proposed by Brander and Prenio. The idea is to capture the essence of converting free states to free states only in an asymptotic sense. And the motivation is similar to the axiomatic definition of adiabatic operations in thermodynamics. So with this motivation, Brander and Prenio introduced a class of operations called asymptotically resource non-generating operations, which is a sequence of operations acting on n-fold systems, such as for any sequence of free states, the resulting state has a asymptotically vanishing amount of resource measured in terms of generalized robustness. Here, generalized robustness is a particular resource measure defined using this convex optimization problem. We are given some state for the state rho. We choose another state rho prime, and so that their convex mixture should be within the set of free states. And it's for the rest of this talk and formulation, it is important to work on this particular resource measure as a measure to define asymptotically resource non-generating operations. Then Brander and Prenio showed that proposed that under general class of Brander and Prenio consider a general class of quantum resource theories, where the set of free states that can be derived from free operations should satisfy certain properties. That is, the set of free states should be finite dimensional, closed, and convex. Should closed under tensor product, should include some full rank states and other two conditions. Then with this condition, we can use it turned out that we can use a particular entanglement resource measure called regularized relative entropy of resource as entropy in thermodynamics. In particular, it was known that if the generalized quantum Stein's lemma, as I explained in the next slide, holds true, then we have a universal framework equipped with the second law, in the sense that asymptotic conversion rate under asymptotically resource non-generating operations should be characterized by the ratio between the regularized relative entropy resource. In this way, if the generalized quantized time theorem holds true, we will have a universal framework with regularized relative entropy of resource, taking the role of entropy in the second law of thermodynamics, which fully characterizes the convertibility between the resource states. So here's a setting of generalized quantized time lemma. So generalized quantized time lemma is a lemma to characterize the optimal performance of a variant of quantum hypothesis testing task to distinguish between some quantum resource state and non-resource state. In this task, we are given an unknown state, and we perform two outcome P of n measurement to distinguish that whether it's a resource state or free state. In particular, the unknown state should be we need to distinguish that whether the given state is n IID copies of some resource state rho, or it is some free state on the n-fold system. And importantly, this free state can, in general, be in a highly non-ID form from a convex set of from a set of free states, which will be chosen as a convex in the setting of generalized quantized time lemma. For example, the entangled state defined for n-fold state is highly non-IID. In this hypothesis testing task, we can define two different error parameters. One is the type 1 error, and the other is a type 2 error. Type 1 error is a error such that we are indeed given the resource state, but we misidentify it as a free state. The type 2 error is we are indeed given some free state, but we misidentify it as a resource state. In the setting of generalized quantized time lemma, for some error parameter epsilon, we want to keep type 1 error below some error parameter epsilon, and we want to minimize the type 2 error as much as possible. It is known that as n increases, this type 2 error can be reduced exponentially in n, and its exponent characterizes how fast we can discriminate, how good we can discriminate these two cases. The question that generalized quantized time lemma addressed is the optimal exponent R. But the challenge in this analysis is the highly non-ID structure of the set of free states. Due to this non-IDness, it's been very challenging to analyze this hypothesis testing task. Nevertheless, Brandon and Perenio originally analyzed this task and then claimed the following. Assume that a set of free states satisfies the previous 5 conditions. Then for any error parameter epsilon chosen between 0 and 1, then the optimal exponent of type 2 error should be exactly characterized as a regularized relative entropy of resource. This provides the operational meaning of regularized relative entropy of resource, and this means as an optimal exponent in this hypothesis testing task. In the special case where the set of free state is only composed of IID states, this reduces to the conventional quantum time lemma for distinguishing two IID states. In this sense, this is a generalization of this time lemma, the conventional quantum time lemma. So here's a small brief history, a very rough history of this lemma. So originally, Brandon Perenio proposed it in Nature Physics paper 2008, and its full proof appeared in 2010. But more recently, some logical gap was found in the part of Fangor-Wang's paper, but this part was based on Brandon-Perenio's original proof. Based on this, more recently, Berta, Brandon, Gorlami, Perenio, Regular, Tomichel pointed out the logical gap of the analysis of generalized quantized lemma in its original paper. Earlier in 2024, with Kodai Kuroiwa in the University of Waterloo, we tried to provide the original proof or alternative proof to fix this issue using some continuity bound on quantum relative entropy, at that time proposed by Bloom, Chappell, Gondorf, Perez, Hernandez. But so this paper was also almost correct, but unfortunately, there are some issues in our analysis. So some logical gap was later pointed out by the author of the previous paper. So in this context, prior to our work, there are many works that try to avoid the issue of using general competence standard lemma by defining some operations not within the set of CPDP maps, but beyond the law of quantum mechanics to avoid this issue. But it's been very challenging to fix this lemma in its original form. So here's the main results. Here's the main result. We provide a proof of a stronger version of generalized quantum Stein's lemma. So our proof techniques eliminate some of the assumptions that was originally required for using quantum definite theorem in their analysis, but our proof does not require this. So Ludovico Lamy also proposed alternative proof of the previous version of this lemma, but this imposes all the 5 assumptions. Maybe Ludovico will explain it in the next talk, I think. But the difference is that our proof technique does not require some of this. And also using this, we also provide a more general framework than the framework of quantum resource theories that is also applicable to a fundamental class of dynamical resources represented by CQ channels, classical quantum channels. In this way, we open a way to formalize and utilize a more generally applicable framework of second law using a stronger form of generalized quantum Stein's lemma. So I would like to explain how we proved the generalized quantum Stein's lemma. So the statement that we proved is that under the assumption of the set of free states satisfying finite dimensionality, closedness, and convexity, and also closed under tensor product, and includes the full rank states, then for any epsilon between 0 and 1, its optimal type 2 error exponent should be given by, it's exactly characterized by regularized relative entropy of resource. The proof is composed of 2 parts. One is a strong converse part to show the optimality, and the more challenging part is a direct part to show the achievability. So the existence of a limit on the left-hand side beta is not a priori obvious. We don't assume anything on this, but this can be seen from the existence of a limit on the right-hand side of the right-hand side due to the subjectivity of the quantum relative entropy. So the limit of the right-hand side exists, and since left-hand side coincides with the right-hand side, left-hand side's limits should also exist. So the important observation, before going into the detail of the proof, the important observation is the characterization of this operational quantity beta by minimax theorem, which basically shows that min and max can be commuted in a setting. In the setting of generalized quantum Stein lemma, what we minimize is the worst case type 2 error, where we have a min and max in this order. But apparently different quantity is a minimization of that of minimizing type 2 error for each state. In this case, max and min appears in a different order. In the most general case, where we don't assume anything on the set of free states, this minimax inequality should hold. But when the set of free states is convex and compact, we can show that these 2 quantities should coincide. So we can work on the quantity with max and min interchanged, and this simplifies our analysis a lot. So instead of analyzing the beta directly, for the f directly, we work on the quantity defined on the right. With this characterization in mind, we provide a simple proof of the strong converse. The proof of the strong converse also appeared in Brandon Perenio's original analysis, and this is valid, and this is valid to my understanding. But this required additional assumptions that our proof, and our proof eliminates such an assumption. To this end, for each fixed m, we take some optimal n-fold non-ideal states in minimizing regularized relative entropy resource. And to bound the operational quantity beta, we consider to upper bound it by some additive quantity. For this purpose, we extend the n-fold free state by using some small reminder part. Then, using this state, we show a simpler derivation using an additive upper bound given by the quantum relative entropy of this operational quantity beta. In particular, using some conventional technique originally developed by Oga and Nagaoka, and also later developed by Koni, Mosoni, and Wilde, this quantity beta is upper bounded by some additive quantity using relative entropy. And then the max of beta can also be upper bounded using this additive upper bound. And in the end, we can show that this is upper bounded by regularized relative entropy of resource. So this is a more simpler part, and the more challenging part is a direct part to show the achievability, where the original proof has some logical gap. So the goal here is that the beta should be lower bounded by the max of beta should be lower bounded by some mean of d, and to analyze this quantity, we fix some optimal sequence in maximizing beta, and also consider any suboptimal sequence in minimizing d. And as in the same way as a strong converse proof, for some very large fixed m, we fill in the remainder by some full rank states. The idea here is that the idea here is that we identify how to from these two sequences, we identify how to construct the optimal sequence in minimizing d from the sequence of states maximizing beta. To do this, we prove some lemma showing that, as I will describe in more detail in the next slide, showing that for any fixed parameter between 0 and epsilon, we can indeed update the suboptimal sequence rho free n to a more optimal one by mixing the originally chosen rho free n and the optimal sequence of states maximizing beta and the full rank states. Using this update, we can show that the difference suboptimality between d and beta can be reduced after this update. Then, applying this update k times, we can show that this difference can be arbitrarily close to 0. And by taking an appropriate limit and subsequence, we can show that we can construct an optimal sequence minimizing d. This should achieve this goal. So the most technical part is a technique to prove this update. So the goal here is that we have a d defined for two non-commutative operators, and we want to show that this updated sequence has a small difference, is more optimal than the original one. We use the two techniques to show this. One is pinching, the other is the information spectrum method, as I will explain in the next slide. The first technique, pinching, is the technique to make non-commuting operators appearing in D commute. So originally we have a row free, so we have this updated state, and this is defined for the exponentially large dimensional space in terms of n. So it has exponentially many different eigenvalues. But we round up and down this. We perform rounding of these eigenvalues to form some approximate state that only has a polynomially different number of polynomially different eigenvalues. Then for this rounded state, we define some pinching map, which is a dephasing map using a projection on each of these polynomial number of eigenspaces. So after the rounding, the state has only a polynomial number of eigenspaces, and using the projectors on these eigenspaces, we define pinching maps. Then what we can show is that after these manipulations after this modification of second and first arguments, we can still show that after the regularization, this limit is not disturbed. So the difference from the previous approach is that In the previous approach, the previous approach tried to use quantum definite theorem. So we have a very large symmetric state, trace out some part of it. So the remaining state almost looks like IID state, up to some small difference in terms of trace distance. Then, especially in our previous analysis, we tried to use some continuity bound on the second argument of the quantum relative entropy, but this disturbs the quantum relative entropy too much. So basically, this does not work. The approach based on continuity bound for trace distance does not work when approximation is on the second argument. By contrast, we can modify this state. We can modify the eigenvalues of this state and perform pinching. And then this does not. It turns out that this is a right way to deal with this quantum relative entropy and does not disturb D too much. So now that we set a new goal, so we have a goal. The goal here is now define the similar inequality, but for the mutually commutative operators. Then to analyze these commutative operators, we use information spectrum method. This is basically a method to convert bounds on beta in hypothesis testing into the probability bounds when we project the state onto the typical subspaces. So using information spectrum method, we start with the definition of quantum relative entropy. But at the core of our analysis, we define some projectors due to using this information spectrum method, and using a probability bounds obtained from quantum information spectrum method. We decompose the right-hand side into 3 parts. We can analyze each of the terms using the commutativity of the operators. So the commutativity simplifies the analysis a lot, and in the end, we can show the desired inequality for the update flow. So using this technique, we provide a full proof of generalized Stein lemma. So in the rest of this talk, I would like to discuss what we can say from this generalized Stein lemma, especially in the context of quantum resource theories. Due to the previous work, it was known that by using the generalized Stein lemma, we will have the second law for the conventional quantum resource theories defined for states, which is called static resources. But the question that we are interested was that how general can we formulate such a framework with second law beyond the conventional class of quantum resource theories? Now, since the time of the original proposal, the applications of quantum resource theories are now much broader. Now it can be applied to analyzing channel capacities and some communication tasks. And for such an applications, we need quantum resource theories for converting channels, which is called dynamical resources. But there's a challenge. But the challenge in this generalization is that quantum channels are usually much harder to analyze because it has unknown inputs, unlike quantum states. So to address this point, we work on a setting of generalizing quantum states to a restricted class of channels called classical quantum channels, or CQ channels for short. So with this restriction, it turned out that we can avoid hardness of analyzing general channels with quantum inputs, but still we can formulate a well-defined and more general framework of quantum resource theories. That includes state case as special case when the input of the channel is one-dimensional. So in our formulation, we choose free operations as a restricted subset of operations that converts CQ channels into CQ channels. This is a subset of superchannels. And free CQ channels is defined as those obtained from any potentially non-resourceful CQ channels by free CQ by free operations. that is CQ to CQ superchannels. Then resource CQ channels are non-free ones, and the conversion rate is defined as the optimal rate to convert between CQ channels, where the error is measured by trace distance between choice states. Then, in the same way to the state case, we try to identify the right class of operations to formulate the second law. So we define asymptotically free operations with the following properties. The first property is analogous to the asymptotically resource generating operations in the state case. So it should be asymptotically resource non-generating in terms of the generalized robustness defined for CQ channels. But we also needed additional condition in a framework, that is asymptotic continuity, saying that for any CQ channels that is asymptotically close to each other, then after its conversion, it should still be close. In the state case, we do not need to explicitly impose this condition, because this is automatically satisfied. But it turns out that in analysis, we need to explicitly assume it, because this does not generally hold for channels. In this way, we identify an appropriate class of superchannels for which second law of quantum resource theory should hold. Using this formulation, under the asymptotically free operations, we show the framework equipped with the second law that is applicable to any CQ channels, so including existing state case as a special case. In particular, we assume that the set of free CQ channels should be finite dimensional, closed and convex, closed under tensor product, and satisfy a certain Fourier condition. Then the convertibility between CQ channels is fully characterized by a single function describing, representing its amount of resource for any CQ channels. And for this resource measure, we can use the generalization of regularized relative entropy of resource defined in terms of choice states of the CQ channels. The proof of this is also composed of direct part showing the achievability and the converse part showing its optimality. For the state case, this has already been shown, but our contribution here is to clarify that this can be generalized to a fundamental class of dynamical resources represented as CQ channels. For the direct part, the key part is an extension of the previous results, clarifying the relation between regularized relative entropy of resource and the robustness measure. Previously shown for states, but we extend it to CQ channels. So this contains a non-relation for state case as a special case when we consider class of CQ channels with one-dimensional inputs. But our result is, in some sense, stronger than the existing one, because existing one does not show the limit, existence of minimum and the limit, but we explicitly address their existence to simplify the analysis. So with this lemma, we show that we can construct asymptotically free operations achieving the optimal rate in the resource CQ channels conversions. In the construction of these asymptotically free channels, we are given some unknown. We are given some channel. Then we input some maximally entangled states to form some choice state. Then we perform two-outcome POVM determined by generalized quantum Stein's lemma. If the input is a resource, we output some corresponding converted resource. But if it's free, we output some almost free thing. So to guarantee that free CQ channels should be converted into free CQ channels up to small resource. In this way, we extend the second. So this construction reduces to the non-construction for the states when the input is one dimension. In this way, we extend the second law framework from states to CQ channels. So then you are represented class of dynamical resources. In the converse part, we want to show that any achievable rate under this asymptotically free operation should be upper bounded by the ratio of these resource measures. So in the case of under free operations, it is well known that the asymptotic conversion rate is upper bounded by the rate of regularized relative entropy of resource. But this technique is not straightforwardly used in the case of asymptotically free operations because for each operations in this sequence, it may slightly generate resource. So the monotonicity is not directly used in this setting. So nevertheless, we show an asymptotic version of monotonicity of the measure that we are using between choice states. So this measure should satisfy a desired property of an asymptotic version of monotonicity required for the resource measure. And to prove this, we needed to impose asymptotic continuity. And then using this monotonicity, we can show that this the optimal rate should be the optimal rate of the conversion is upper bounded by the ratio of these two measures. So in the rest, I would like to discuss what this could imply. So these results revive essential tools for the general framework of quantum resource theories. I think this provides vast implications for the analysis of quantum resources. One interesting thing that I would like to discuss is the optimal overhead in magic state distillation. So under the asymptotically resource non-generating operations, this result shows that asymptotic conversion rate from noisy state to the magic state is exactly given by the ratio of the regularized relative entropy of magic. So in another work, we recently showed that under stabilizer operations, the overhead of magic state distillation can be asymptotically non-zero. But at the moment, it's very hard to characterize the optimal rate under the physically relevant stabilizer operations. But the important thing is that if we relax the class operations, we can fully characterize this optimal overhead, even in the magic state distillation, beyond entanglement theory. And also, the generalized content lemma by itself has many applications in quantum inference theory. For example, the faithfulness of scarsal entanglement. Now we have an alternative proof, but originally proven using this result. And I believe that there still is many other applications of the Stein's generalized content lemma in the quantum information theory in general. In this way, I believe that proving generalized content lemma is not the end of this problem, but it's merely a first step in its vast applications. Finally, I would like to briefly discuss what this could imply in the case of magic state distillation as one example. So we recently showed that magic state distillation can be achieved within constant overhead under the stabilizer operations. And similar to LOCC in entanglement theory, this is based on a bottom-up approach by defining operations as what we can do in the lab. So in this case, we define stabilizer operations as a class of operations composed of preparation of Ket0 state, Clifford gate, and Z-based measurement. And then we managed to prove that non-zero asymptotic conversion rate from noisy state to magic state is possible. But the current construction is not optimal in terms of constant factors, and it's very challenging to optimize these constant factors. But if we take an alternative top-down approach and consider the setting of generalized content science lemma, we can define asymptotically resource non-generating operations in the conversion of the set of stabilizer states. And then in this case, we have an exact characterization of the asymptotic conversion rate given by the ratio between regularized relative entropy of magic. So there are many works on the application of quantum resource theory of magic, for the magic state distillation, but most of the work address the converse bounds, showing the fundamental limits in their analysis. And this Stein's lemma provides a very rare case of addressing achievability, albeit it's currently a bit artificial class of operations. And so the important open problem, I think, is information theoretic method to address achievability of optimal rate of magic state distillation and the stabilizer operations, or how much we can address this using the techniques in the quantum resource theories. Finally, from the broader perspective, I'd like to briefly introduce what I've been doing in my research. So throughout my research, I've been trying to lay a theoretical foundation to connect the advance of content technology to our advance of our IT society. So to do this, I work on several different things, including quantum algorithms, quantum error corrections, and also quantum resource theories, as I talked in this talk. But in my view, these are closely related in many aspects. For example, we recently showed a provable quantum advantage in solving learning tasks. And one of these works is highly related to quantum thermodynamical techniques. And also, we analyzed we developed quantum algorithms for quantum machine learning, but its analysis turned out to be highly information theoretic to bound its achievable runtime. And also, I work on several different things on Fortran quantum computation. And as I talked, especially for the magic state distillation, for the analysis of magic state distillation, quantum resource theoretical technique would be highly useful, as I expect. And I also previously worked on general formulation of quantum resource theories, and I'm very happy to present these results in this conference. So in summary, we proved generalized quantum Stein's lemma with a much smaller assumptions than previous work. Using this, it turns out that the second law of quantum resource theories holds not only for states, but also a representative class of dynamic resources given by CQ channels. In this way, the universal axiomatic framework for quantum resources is now available, much like thermodynamics driving our technological advances ever since the Industrial Revolution. So it will be an exciting time to explore the more applications of these results. Thank you for your attention.
Okay, thank you for a very nice talk. We have some time for questions. Andreas?
Yeah, I don't know if I need a micro. Can you hear me like that?
The microphone for the recording.
It's better. Okay. Just let me know. Can you comment on the possible generalization of the channel version to general channel?
General channels. So we initially tried to work on general channels, including quantum inputs. But there's an issue in the achievability part. So if you open our paper, we have a footnote where the issue occurs. So I'd be very happy if we could discuss it further. So yeah, so there's some single line that is very hard to address.
Thanks for the interesting talk. I also have a question for the application to the CQ channel part.
Yes.
So you use the distance between the choice states in the definition of the asymptotically non-generating operations. Do you think a second law could also happen if you use the diamond norm as a distance measure there?
Indeed, we're working on that. We are trying to finalize. So we also have a generalization. So we are working on finishing this. So please stay tuned.
Okay, thanks.
Yes, it's possible, but we need a different formulation. And yes.
Okay, we have time for maybe one more question while the next speaker sets up. Or not, then in which case we'll thanks Hayata again.